Hello everyone and welcome to the second video lesson for Chapter 5 of the Foundations of Scalable Systems. Let's start talking about designing services. We deploy our service implementations in application servers. An application server is a container that's deployed to handle API implementations. The server receives requests and routes them to the appropriate handler function to process the request. The handler is defined by the application service code and implements the business logic required to generate results for the request. As multiple simultaneous requests arrive at a service instance, each is typically allocated an individual thread context to execute the request. The sophistication of routing functionality varies widely by technology, platform and language. For example, in Express.js, as shown on the slide here, the container calls a specified function for requests that match the API signature, known as a route path, and HTTP method. The code example on the slide illustrates this with a method that can be called when the GET request arrives for a specific skier's profile, as identified by the value of skier ID. In Java, the widely used Spring framework provides an equally sophisticated method routing technique. It leverages a set of annotations that define dependencies and implement dependency injection to simplify the service code. The code snippet on the slide shows some of these. The REST controller annotation identifies the class as a controller that implements an API. The GET mapping maps the API signature to a specific method and defines the format of the response body. And the path variable identifies the parameter as a value that originates in the path for a URI that maps to this method. Another Java technology, the Java Enterprise Edition Servlets, also provides annotations, but these are simplistic compared to Spring and other higher-level frameworks. The @web servlet annotation simply identifies the base pattern for the URI, which should cause a particular servlet to be invoked when a request arrives. The class that implements the API method must extend the HTTP servlet abstract class and override at least one method that implements a HTTP request handler. The four core HTTP verbs map to servlet methods as shown here on the slide. Now let's move on and look at the issue of how services manage states. State management is a tricky, nuanced topic. The bottom line is that service implementations that need to scale should avoid storing conversational state. What on earth does that mean? When a user or application connects to a service, it will typically send a series of requests to retrieve and update information. Conversational state represents any information that is retained between requests such that a subsequent request can assume the service has retained knowledge about previous interactions. Let's illustrate this with a little example. For example, the skier service API that we've been talking about, a user may request their profile by submitting a GET request to the following URI. They then may modify the returned values from the GET request to update their city attribute and send a PUT request back to the service. Note this URI does not identify the skier ID that's associated with the request. Hence, the service must know the unique identifier of the resource to update, namely 768934. Hence, for this update operation to succeed, the service must have retained conversational state from the previous GET request. Implementing this approach is pretty straightforward. When the service receives the GET request, it creates a session state object that uniquely identifies the client connection. In reality, this is often performed when a user first connects to or logs into a service. The service can then read the skier profile from the database and utilize the session state object to store conversational state. In our example, this would be a skier ID and likely values associated with the skier's profile. When the PUT request arrives from the client, it uses the session state object to look up the skier ID associated with this session and uses that to update the skier's home city in this example in the database. Services that maintain conversational state are known as stateful services. Stateful services are attractive from a design perspective as they can minimize the number of times a service retrieves data, the state, from the database and reduces the amount of data that is passed between clients and services. As you scale service implementations, however, the stateful approach can become problematic. For a single service instance, you have two problems to consider. First, if you have multiple clients all maintaining session state, this will utilize available service memory. The amount of memory utilized will be proportional to the number of clients the service is maintaining state for. If a sudden spike of requests arrives, how can you be certain we will not exhaust the available memory in our service and cause the service to fail? Hard to know. You've also got to be mindful about how long to keep session state available. A client may stop sending requests but doesn't cleanly close their connection to allow the state to be reclaimed. All session management approaches support a default session timeout. If you set this too short, then clients may see their state disappear unexpectedly. If you set the session timeout period to be too long, you may degrade service performance as it can run low on resources. Stateless services, however, maintain no conversational state, as shown on the slide here. We send a GET request to our service, it retrieves our profile, and then returns the profile as part of the response to the request. Then the updated skier profile is sent via a put operation with the skier identifier associated in the URI. This is then used to update the profile and return a success. The service itself maintains no conversational state. Any scalable service will need stateless APIs. The reason will become clear when I explain horizontal scaling later in these lessons. For now, though, the most important design implication is that for a service that needs to retain state pertaining to client sessions, the classic shopping cart example perhaps, this state must be stored externally to the service. This invariably means in a data store, a database. APIs are implemented by code that you write and deploy to a service. Services are typically executed in the context of an application server. Let's look at these beasts in more detail. Application servers are the heart of a scalable application, hosting the business services that compose the application. Their basic role is to accept requests from clients, apply application logic to those requests, and reply to the client with the request results. The technological landscape of application servers is broad and complex depending on the language you want to use and the specific capabilities that each offers. Some of them are listed here on the slide. In the Java world, Apache Tomcat is an open source implementation of a subset of the Java Enterprise Edition platform and mostly is used for implementing Java servlets. This slide depicts a simplified view of the anatomy of Tomcat. Tomcat implements a servlet container, which is an execution environment for application-defined servlets. Tomcat dynamically loads servlets into this container and it provides lifecycle management and a multi-threaded runtime environment. A Tomcat server listens on a particular IP address on port 8080 for HTTP requests and port 8443 for HTTPS requests. If a network requests arrive at a frequency that cannot be processed by the TCP listener, pending requests are queued up in the socket backlog, and in most Linux systems the default size of this backlog is 100. Once a connection is established, the TCP requests are marshaled, in this example by the HTTP connector, and this generates HTTP requests that could be passed to the servlet. The HTTP request is then dispatched to an application service container thread to process. Application container threads are managed in a thread pool, which by default in Tomcat is a minimum size of 25 and a maximum of 200. In processing the business logic, servlets may need to access an external database. When a servlet thread wishes to submit a query to the database, it requests a connection from a database connection pool which can be supported by Tomcat. If a connection is available, access to the connection is granted to the thread until it indicates it has completed the work. At that stage, the connection is returned to the connection pool and made available for other servlets to utilize. An application server framework such as Tomcat is hence highly configurable for different workloads. For example, the size of the thread and database connection pools can be specified in configuration files that are read at startup. The complete Tomcat container environment runs within a single JVM. and hence processing capacity is limited by the number of virtual CPUs available and the amount of memory allocated as heap size to the JVM. Each allocated thread consumes memory, and the various queues in the request processing pipeline consume resources while requests are waiting. This means the request response time will be governed by both the request processing time in your servlet business logic, as well as time spent waiting in queues for threads and connections to become available. When a Tomcat servlet becomes heavily loaded with many threads allocated, context switching may start to degrade performance and available memory may become limited. If performance degrades, queues grow as requests wait for resources. This consumes more memory. If more requests are received than can be queued up and processed by the server, then new TCP connections will be refused and clients will see errors. And if requests keep arriving at your server faster than they can be processed, the servlet may run out of resources and start throwing exceptions and eventually crash. This means that effort expended tuning configuration parameters to efficiently handle anticipated workloads is rarely wasted. Systems tend to degrade in performance well before they reach 100% utilization. Once any resource, CPU, memory, network, disk, etc., gets close to full utilization, systems exhibit less predictable performance. This is because more time is spent on time-wasting tasks such as thread context switching and memory garbage collection. This inevitably affects latencies and throughput. Thus, having a utilization target is essential. Exactly what these thresholds should be is extremely application dependent. Java-based application frameworks such as Tomcat support the Java Management Extensions (JMX) framework, which is a standard part of the Java Standard Edition. JMX enables frameworks to expose monitoring information based on the capabilities of mbeans, managed beans, which represent a resource of interest such as a thread pool or a database connection pool. This enables an ecosystem of tools to offer capabilities for monitoring JMX-based platforms. Monitoring tools range from simple applications such as JConsole, which is shown here on the slide and is available as a standard part of the JDK, to much more powerful open source technologies such as Java Melody and many expensive commercial offerings. So this lesson has covered the basics of the application server technologies that we use to host our business logic. What I'm going to do next is look at how we scale out these individual service instances using horizontal scaling. Thanks for watching.